Dear friends, dear participants, let me introduce you Ned Block from New York. And many thanks for Professor Ned Block to join our section at the conference with his presentation about non-conceptual color perception.
Okay, so let me start with something that wasn't in the chapter. A psychologist named Michael Cohen did this wonderful experiment where he hooked up. Can you see my arrow?
Yes,
Do you
yes,
see my?
yes.
Yeah. He hooked up a eye tracker to subjects, and then what he did was he took a stimulus like this and he blanked out the color everywhere except where the person was looking. So using an eye tracker, you could do this wherever you were looking, the color would be blanked out in all the other places. And what he found is quite a few people didn't notice the lack of peripheral color, that is, color outside of the place where they were actually pointing their eyes. And this is a well-known result now that many people have replicated, and it gives rise to an interesting question. Well, why is that? So why do people fail to notice the lack of color in the periphery of their vision? So there are two answers, and the two answers are it's because they don't have actual color perception in the periphery of their vision, or they just don't have cognition. They don't think about the colors in the periphery. And this is a basic distinction having to do with this issue of how we distinguish perception from cognition. By cognition, I mean thought, reasoning, and that kind of thing. And so this is a crucial point from my perspective. So the sparse perception view says that our perception in the periphery is vague, gisty, if that's a term that they use. Sometimes they use the term ensemble perception. It just gives you kind of averages, and those averages are so weak that they don't distinguish between color and no color in the periphery. The alternative, which I favor, is that we see the colors in the periphery, but we don't cognitively register the difference between color and no color. So that's a really basic disagreement about color perception in the periphery of vision. So that's the one that I like. According to Cohen, these two pictures look the same given where given that you're looking at the central figure. According to me, they look different, but the viewers don't apply the relevant concepts and so don't cognitively register the difference. So that is the key difference here. Is that difference clear?
Yes, yes.
Okay. So I think there's a certain kind of fallacy I call the sparse perception fallacy, which is in cases where the subjects don't cognitively register a difference, people think the items don't look different. But the alternative explanation is they fail to apply color concepts. So what I say is the subjects don't distinguish those two pictures because they don't apply color concepts. And this is where the infant color perception stuff comes in, because there's a parallel. Adults don't distinguish these because they don't apply color concepts. Infants between 6-month-olds and 11-month-olds, according to me, see color, don't normally cognitively register color differences because they don't apply color concepts normally. Now, that leaves open whether they have the concepts but don't apply them, or they don't have the concepts. I'm not so concerned with which is true here, but I think that the likely answer is item 2. Now, in the chapter that you are supposed to have read, what I say is the argument is not that infants do not ever have color concepts or proto-concepts of color, but rather that in normal circumstances, they see colors without activating any such concepts. If the color perception were conceptual, the concepts would have to be activated. And so this is all part of an argument that color perception, in fact, all perception is not conceptual. So the main point of chapter 6 is that 6 to 11-month-old infants do not normally apply color concepts in the perception of color, so those perceptions have to be non-conceptual with regard to color. And then I try to generalize to all perception and also to adults. So according to me, these are the three types of representation of color. At 4 to 6 months, infants begin to get color category representations. At 11 to 12 months, they begin to get color concepts. And then it takes until roughly 3 years until they get linguistic color concepts. So just to be clear, by concept, I mean a conceptual representation, a representation in the mind that is used in thought and reasoning. That's what I mean by a concept. Any question about that?
I think no.
Okay. So these are the three main ages I'm talking about. 4 to 6 months, they can see color, and they have color categories. 6 to 11 months, they have color perception without color concepts. 11 to 12 months, the beginning of color concepts. So what is this categorical perception? So this is a diagram of sound labeling in English. And this is concerned with the difference between B as in boy, D as in dog, and G as in God. This is along this axis, we have a stimulus value. Doesn't really matter too much what it is. And this is on this axis, the percent identification. And what you see is there are pretty sharp boundaries. So in particular, 2 instances of D at values 5 and 7 sound much more similar than 2 instances of the sound between 9 and 11, where one sounds like a D and one sounds like a G. And the same is true in every language, that there are babies come born with able to make many distinctions, and then once they learn their native language, they lose the ability to make certain other distinctions. But we can see this categorical perception in, for example, the rainbow, which is a continuous band of colors, but looks like stripes. The behavioral signature of this is faster and more accurate discrimination between than within categories. So it's easier to distinguish red and yellow from 2 shades of red if they differ both by the same amount, say 40 nanometers. And the 2 reds will look more similar. Okay, so this kind of categorical perception can be used to diagnose the color categories of infants. And Anna Franklin at the University of Sussex showed that if you show adults or children a uniform screen with a disk of a different color, if the person sees it as a different color, they tend to move their eyes to it. And they move their eyes faster if the colors are in different categories. And you can use that to map the color categories of adults and children. Another method for doing this is the method of habituation. So you find if you if you show a child or an adult a screen with something on the left and something on the right, this is one presentation, another presentation, another presentation, another presentation. This is called familiarization, where you have the same thing again and again and again. And what happens when you do that is the child stops looking at the screen, gets bored and stops looking at the screen. But then if you have a different color, the child starts looking at the screen again. And the amount of how long the child will look when it's a new color can be used to gauge color categories, just like the one we just saw, just like this one. The idea is that novelty preference is greater for different categories. Is that clear?
Yes.
Yeah, okay. And it turns out that different methods, there's some other methods as well, use the same category, and these are what Anna Franklin found and her colleagues found doing tests on infants all over the world. Russian children would be just the same as American children. And they are these 5 color categories. And in this diagram, these count as the same because there's lines between them, but these count as different for babies. And you can, and then they also did it for many adult groups and found that the boundaries were different for adult groups and different in different languages. And of course, one difference between Russian and English is that you have different words for light blue and dark blue, and we only have one single word. Just we call them both blue. So the question arises: do these 6 to 11-month-old infants attend to color or notice color? And I think this shows a certain kind of noticing, but it doesn't show cognitive registration, since there need be no thought or reasoning involved. It does show attention, and it turns out that categorical perception requires attention. It's shown by my colleague David Heeger. So they attend to color, but that doesn't show that they think about color or have color concepts. Okay, so I finished talking about color perception. That's about color perception. Now I'm going to turn to the failure of the same children in color cognition. So this all illustrates the distinction between perception and cognition. These 6 to 11-month-olds can see color perfectly well, but they cannot do cognition of color. And one a wonderful example of this is an experiment by Jean-Remy Hochman, where what he did was he showed babies of various ages a screen. This is the center of the screen, and they had something on the left and something on the right. And what he found was if he set it up so that if the thing on the left and the thing on the right were the same shape, that predicted say a jumping frog that made a great noise. The children can learn that rule, that the same shape predicted look to the left or look to the right, depending on the experiment. But they could not learn. They were only, at 12 months, they were only beginning to learn that same color predicts something interesting. So they can learn a rule about shape, but not color. So that's a really significant result. And that's quite a general result. Shape and other kinds of information about something are used in cognition well before color is used in cognition. So this requires some kind of a concept or proto-concept of color, not just concepts of specific colors. Another type of experiment, Shu, Carey, and Welsh, showed infants a screen with something coming out one side and something coming out the other side, and then the screen went down and they found that under 12-month-olds, the infant does not expect two things. And the general result is that babies use shape and kind information in forming expectations about number months earlier than they use color. And in that period, they don't normally reason using color representations. Here's a more complete diagram. A screen, an object, a truck is brought out, goes back. Some kind of an animal, looks like a cat, comes out and goes back. When the screen goes up, the children don't expect, don't show any surprise when there's only one thing. So it looks like they learn to do that much faster than if there are two different colors. And another thing is in that experiment, I guess I thought I had a slide on this, but I don't, that if they know the words for duck and truck or whatever animal it was, then they do notice the difference much more easily. So I mentioned in the book that I say the results just described involve a contrast between color and shape and kind, and perhaps color just isn't as salient as shape and kind. And I said perhaps, but I would now say definitely. And the salience does provide an explanation, but the question is, why is color less salient? And I think the reason why color is less salient is in part because they lack the color concepts. And so I do have this slide. If they could use a duck and truck, then they typically knew the words for duck and truck, suggesting knowing a word makes the referent more salient. And when they get older, some glimmers of the concepts of color may help in color. So here is a different kind of experiment, very similar to this is Trimley, Leslie, and Hall. In this experiment, forget about this side, that's just the control. So if one shape comes out and goes back, and another shape comes out and goes back, under 12 months, they're surprised if you see two things of the same shape, but they're not surprised if you see two things of the same color. So that's another experiment that shows failure to reason with color. Any question about that?
Yes, I have one question on understanding. So, why infants can't use the categorical differentiation for operating the figures with different colors, don't with some cognitive abilities, high order cognitive abilities, but with some low order cognitive abilities, with some reactions, maybe they can understand their own reactions on different colors and then understand that these colors are different.
Yeah, you're supposing what's often called metacognition in these babies, that they can pay attention to their own reactions. Babies are very poor at metacognition. And given that they normally lack color concepts, they just can't use any color information in reasoning unless they're given specific training or the colors are made particularly salient in one way or another. So you can get children to use color information if you do various kinds of training.
But in that experiments in which they didn't operate with colors, they can, with categorical abilities, differentiate colors with attention. Yeah,
that's right. Yeah, their attention shows the difference, but not their cognition.
Okay.
Here's another experiment. This is by Wilcox. And this is, you have a very narrow screen. You have a ball rolling towards the screen. You can see a hand there moving it. And then it goes behind the screen. The screen is just the width of the ball. And then something of another color comes out. And they use real objects in this, not simulations on a screen. And what Wilcox found was that at 4.5 months, they show increased looking time compared to a wide screen if a ball turns into a box, but not if a red ball turns into a green ball. At 7.5 months, they use not only shape but kind information, like if a duck turns into a truck. It takes until 11.5 months before they can use color normally. So color, this is just another experiment that shows that concepts of color come way later than shape and kind concepts, and well after they can see the color differences. Now, an objection is maybe they have a concept of color that isn't activated. And there is some support for this because training can make the difference. So they did 2 rounds of training at 9.5 months. Then they did look longer at the red ball changing into the green ball. And 3 rounds of training for 7.5-month-olds allowed them to do it. The training was one color was used to pound, and another color was used to pour. Here's a little blow up of that. Green was used to pound in one case, and red is used to pour. Now, interestingly, the 9-month-olds generated from red, green to blue, yellow, but the 7.5-month-olds didn't. So the upshot is that training does increase the saliency of colors. And in the case of 9-month-olds, maybe color generally, maybe by giving them some kind of a proto-concept of color. So my view isn't that infants can't use color concepts. What I said in the book was they don't normally use color concepts. So I've been misinterpreted on this. So I talk about their failure to normally deploy color concepts. So the point is that in a normal instance in which they perceive color without using a color concept, the perception of color must be non-conceptual. So there has to be some non-conceptual perception. Now, an interesting question is, does training change a perceptual representation into a conceptual representation by making the perceptual representation more salient, or does it activate a already present but inactive concept? Now, I'm officially neutral on this, but what I really think is that it changes the first one. It changes a perceptual representation into a conceptual representation. So a conceptual representation is one that has a certain role in reasoning, thinking, other cognitive processes. We can call that the R role. And so then the question becomes, does training give a perceptual representation the R role, or does it activate an inactive R role? But what is an R role? Well, an R role is partly learning rules for color like this one. Same color predicts something, just like the same shape predicts something. So the R role is stuff like that, the use of color in reasoning. And if we ask, does training give a perceptual representation of the R role or activate an inactive R role? It looks like this one is better because there really isn't any reason to postulate a role schema for colors before the child has any active R roles for colors. So I think the R roles are a matter of changing a perceptual representation into a conceptual representation. So we can wonder, maybe the infants have a concept of color as a temporary property of things, and that there's evidence against. So this is a great experiment done by Kimura and colleagues. They had normal faces and weird faces, normal vegetables and fruits, and weird vegetables and fruits. And then they showed colors, they showed flowers, but the flowers don't have a typical color. They come in all kinds of colors. And so these are less weird because although they've changed the colors, that they're not so unusual. And the 6-month-olds prefer to look at the normal colored faces and vegetables, but they didn't care about the flowers. So that suggests that they, to the extent that they have a grip on color, they understand it, or sorry, maybe not understand it, but they're assuming in some non-conceptual sense that colors stay the same, and it isn't a matter of having a concept of color as a temporary property of things. Okay, so these are the experiments some of the experiments I mentioned that suggest that babies do not normally use color concepts in reasoning. We can go back to this question and ask what it is for a perceptual representation to acquire the role of a conceptual representation. And we can approach that through some really quite wonderful working memory experiments. This is done by Clay Curtis. Clay Curtis has done a few of these, and Una Quack is his grad student. And here's what they did. They showed people that, so there's two separate tasks. Looking at this one, grading orientation, they showed them a fixation point, and then there was a grading at some angle or other, and then the fixation point again, and then subjects were supposed to move a cursor to match this to that. And then they gave them feedback. The other experiment was they had a fixation point, and then they had dots with a motion in one direction, and then a delay, and then they had to match a motion stimulus to the original one. And again, they got feedback. And they did this while the subjects were in a scanner, and they had this delay period of 12 seconds while the subjects were forming a working memory representation of what they had seen. And what they found was that in this delay period, the representations were the same. In other words, the subjects threw away information about the dots and represented this as just an oriented line. And the same with this. And what that suggests is that one of the things that happens when we conceptualize is abstraction. We abstract in the service of a task. And similarly, we saw that you needed, for concepts here, you needed abstraction. You needed to abstract away same shape and same color. So abstraction is definitely one thing that happens when you form a cognitive representation. Another thing that happens is there's what's called categorical bias. And one great experiment that showed this showed that working memory representations are more categorical than perception. And the experiment was this. They showed people a display of different colors, and then a fixation point, and then an arrow, and the arrow pointed to where there was a color, like in the case of this one. And then the subjects had to move a cursor to the exact color, and then they had feedback saying, you saw this and not this. And what they found was that working memory representations are more categorical, that is biased towards focal colors, the focal colors in their language. So we see at least two things that are different about concepts. There is a categorical bias, and there's abstraction. So that is at least two differences between color percepts and color concepts. So just to summarize, 4 to 6 month olds see color. 6 to 11 month olds, they have color perception without normally deployment of color concepts. At 11 to 12 months, they get the beginnings of color concepts. A year later, kids can use color to distinguish my toy from your toy, but it takes until almost 2 years old before they do that. And then it's more than another year, at least in the US, before they know the 4 basic color words. So you can see there's a long gap between color perception and color cognition. And the 4 basic color words, red, green, yellow, and blue, Mabel Rice did this experiment. She took a group of 2 to 3-year-olds who knew no color words and tried to teach them the difference between red and green. For most children, learning this difference took over 1,000 trials over several weeks. And it can be very difficult for children to learn color words. And it's interesting that Charles Darwin, I quoted this in the chapter, but I'll quote it again. Charles Darwin famously said, "I attended carefully to the mental development of my young children, and with 2, or as I believe 3 of them, soon after they had come to the age when they knew the names of all common objects, I was startled by observing that they seemed quite incapable of affixing the right names to the colors in colored engravings. Though I tried repeatedly to teach them, I distinctly remember declaring that they were color blind." And this is a phenomenon that was noticed in the early 20th century, was given the name Farbendummheit by a German psychologist. And interestingly, in Binet's early IQ tests in France, he found that children then, in the early 20th century, did not learn the 4 basic color words until they were 7 years old. By 1980, when Mabel Rice was doing her experiments, it was 3 years, 3 months. And some work by David Barner suggests that it's even earlier now. And of course, the reason is plastic. When you compare the kinds of objects that babies see now with the ones that Darwin was talking about, you see that color is just, it's just ubiquitous in our environment now in a way that it didn't used to be. And this phenomenon of children not knowing their color words really surprises parents. There was a Scientific American article about it called "Why Johnny Can't Name His Colors," which said, no, the kid's probably not colorblind. And here's what they found. Parents think their kids do know the colors. And I've tried this out on a lot of kids with their parents. The kids don't know the colors, but the parents think they do. And that's because they have memorized the colors of some common objects. So what they did was, in the experiments reported in this Scientific American article, they did a test with the kids and the parents. And here is a little summary. Before the test would begin, the child's parents were told that today we would be testing color words. Responses were typically enthusiastic. "Oh, that's great. Margie's got her colors down pat." That's the parent thinking that the kids do know their color words. At which point we leveled with them. If they wanted to sit through the study, they would have to be blindfolded. Such measures may seem extreme, but then again, so were the reactions we got from parents during the pilot study as they watched their little ones fail to pick out the right color over and over again. The reactions ran the short line from shocked to terrified and back again. Some parents were so dismayed they started impatiently correcting their children mid-test. One mother in particular couldn't seem to stop herself and took to nervously grabbing her little boy's hand whenever it veered away from the correct choice. Then inevitably would come the post-test breakdown. Is my child colorblind? Divorced from context. So the kids know the color words often in context, where they know what color things are supposed to be without knowing what colors are. Most 2- and 3-year-olds might as well be colorblind. Certainly they look that way when asked to correctly identify colors in a lineup or accurately use color words in novel contexts. What's more, psychologists have found that even after hours and hours of repeated training on color words, children's performance typically fails to notably improve, and children as old as 6 continue to make major color naming errors. This is seriously bizarre when you consider all the other things that children at that age can do: ride a bike, tie their shoes, read the comics, and mistake a blue cupcake for a pink one. Really? Does that actually happen? Apparently, yes. So, just speaking to those of you who may be parents, you may be overestimating your child's color term knowledge. So just to summarize, children can see color at a certain age, but they don't normally cognitively register color. And so it's possible to see color without cognitively registering it. And the sparse perception fallacy is because subjects do not cognitively register a difference, they don't look different. And the alternative explanation is they do not apply the color relevant concepts. And I think that this goes back to the experiments by Michael Cohen that I started with, that subjects don't distinguish these so as long as they're looking at the spot, because they don't apply color concepts, and that's a parallel with the 6 to 11-month-old babies. Now, I'm just going to add one thing that I don't know that was in the chapter about the role of language with color in adults, because I think it's relevant to some differences between different languages, including Russian and English. So this is a 2009 review by 2 people who study color words in different languages. And they asked the question, does language affect perception? As noted above, several studies suggest that the answer is yes, at least in connection with color. These studies have shown that there is categorical perception, CP, faster or more accurate discrimination of stimuli that straddle a category boundary for color, and that differences in color category boundaries between languages predict where CP will occur. And I showed you that diagram where there are different languages have different categorical boundaries when tested on adults. Moreover, several of these studies and others have shown that color CP disappears with a concurrent verbal interference task, like where they have to recite some words while they're doing the color task. And the Regier and Case, they confirming that color CP is language-based. But what they don't really recognize is this is actually evidence against there being a color, a perceptual effect of language on color. And the idea here is that this is supposed to be the word for one of your blue colors. I don't know if I got that right. Is that right?
Yes.
Okay. So I don't know how you pronounce that. Cine. So both the same. Correct. So the point here is that a subject can use color words in making those categorical perceptions, even if the words do not actually affect the color perception. And this point was made in an article on using Russian and English speakers. And the same point has been made using Greek speakers who also have two words for a light and dark blue. And the point they make is this. If the language-specific distortions and perceptual discrimination had been a product of a permanent change in perceptual processors, temporarily disabling access to linguistic representation with verbal interference should not have changed the pattern in perceptual performance. Instead, our results suggest that language-specific distortions in perceptual performance arise as a function of the interaction of lower-level perceptual processing and higher-level knowledge systems like language online in the process of arriving at perceptual decisions. So the point here is that the effect is post-perceptual. That is, that the very marked effects on what's called categorical perception in different in different languages probably does not involve actual differences in perception. It's probably more based in post-perceptual cognitive effects. So the end.
Thank you for Professor Block for this presentation. And so while other participants thinking about the questions, I'll ask my question first. I'm trying to understand the connection between categories in 4 to 6 month infants and between the concepts in the adult age and infants after 11 months. So I think, if I understand this correctly, I think that for to conceptualize something, we need some units to operate. So there should be a unit in color field or maybe color continuum to operate in functional sense. But what exactly units are for this operation? If we think about categories, they are more too broad to operate them as concepts. As if I right understand your presentation, so it's bluish. It's not blue or sini in Russian. It's more broad. It might affect on another colors which is neighbors to the blue or sini, and I think that we need some units or maybe proto-conceptions, proto-concepts, but you use a term proto-concepts in another sense. So my question is, have we any understanding of what exactly precedes proto-concepts in the age of 4 to 6 months? And if we understand it, do we understand the nature of in a very narrow sense of the term nature, of course. So do we understand the nature of this perceptual field or perceptual continuum which we found in infants? Is it discretized, or is it maybe already have any boundaries between colors, but which not used in any functional cognition? Or is it a continuum? And if it is, how we can how perception with a cognitive element can destruct these units in the age of 11 months and earlier?
Yeah, that's a good question. There's many different questions there. So let me just let's see if I can go back to this. So remember this one. where a blue thing can come out on one side and a red thing can come out the other side. And the under 12 months, they don't expect two things. Look, those are two very broad color categories. So it isn't the fineness of grain of the categories that is so important here. It's the under 12 months, even these very broad categories, they're not able to use in reasoning. So I think that what really is going on here is that through some combination of language and perception, they have to abstract away the dimension of color. And that doesn't happen, or at least in 1980, it didn't happen until they were over 3 years old. So exactly how that process works, I do not know, but I don't think it's dependent on the fact that the categories are too broad. I don't know if that's of any use.
Yeah, thank you. And I can see that Andrei can want to ask a question. Please, Andrei.
Yes, thank you, Professor Blok. I have a question broadly about your position in your book. In your book, you accept the state non-conceptualism and not the content non-conceptualism, and you separate the question about the conceptuality and the question about the format. You argue that the perception have iconic format of representation and the cognition, thoughts have discursive format of representation, but you also argue that features, hallmarks, which are usually familiar for the cognitive states, like systematicity of thought or like Evans's generality constraint, they can appear actually in iconic representations when we use iconic representations in reasoning through imagination and so on. So it cannot be used for arguing for the division between the two formats. And your positive marker is the analog magnitude mirroring. An iconic code preserves degrees of variation and a discursive code does not. But this leaves color categorization awkwardly placed because when in just color perception, when stimulus changes, so the corresponding degree of change emerges in the representation. But in color category representation, small change in the wavelength makes no representational difference if this change occurs within the category boundary. And if minimal cross-category boundary appears, then the shift triggers a new category. So it seems like the color category representations does not have the analog magnitude mirroring. So if your way of dividing two types of formats of representations is wherever one has.
I think that's the question. So let me just point out to you the categories are not entirely discrete. What they are is they're smushed and warped. So this is an analog change. It's just very rapid at the boundaries. It's not a completely discrete category.
Yes, but if I'm right, if I'm rightly remember, the burst change in attention occurs then even a little stimulus changes across the category boundary. So it seems like this mirroring is not like we is not the same we usually have in like shape representations or color representations when the change in degree is the same like change in the representational vehicle. In case of categories,
I agree with that. I agree that the the analog mirroring in the case of these categorical representations is warped in a way that other analog mirroring isn't. But that doesn't mean it isn't analog mirroring.
Mm-hmm. Okay, I can see another question, so I'll ask another question about perception and phenomenal aspect of perception. You consider it in one chapter of your book, in 11th chapter, if I remember correctly, and the whole book is not about phenomenality, but at the in the starting thesis of your book, you say that your book, the motivation for considering this theme about perception and cognition is also about difference between phenomenal and access consciousness. So my question will be about it. If I understand you correctly, you suppose that perception in infants and the perception in the part of its overflow in adults is phenomenal. So we have phenomenality without access and without cognitive aspect. And the question about that overflow, how can we explain, or how can we understand this overflow in functional terms? So evolutionary overflow may be explained in terms of mistakes, maybe, or in terms of maybe the evolutionary trace from the processors of humans. So we have that part may be not necessary for our cognition, but we had it because the evolutionary way just left it that for us. But it for me, the all cognitive and evolutionary explanations of perception overflow doesn't work for phenomenal perception overflow, because perception, if it works with a simple, considerably simple physiological ways, in neuronal basis, we can explain it in the way that it's just like physiology works. It's just like the mechanism of perception works. But for phenomenality, which not used in cognitive operations, this answer doesn't work for me, because phenomenality, it can be two ways. We may say that phenomenality needs another mechanism different from perceptual itself, and that brain has that mechanism that makes this perception phenomenal. And another way, we can say that phenomenality is just goes with perception, and we can say why it is. It's just that. So for me, the both ways are doesn't work for explaining why phenomenality overflow, because it shows us that phenomenality is too complex, too very specific thing to just has it without using in our brain. Why evolution make go this way? I don't understand this implication of this reasoning. Do you understand the question?
Yeah, I understand the question. It's a very, profound question, and I don't have the answer. But so what is the function of consciousness? That's really the question. And I think we can. I mean, we can speculate about the function of consciousness. We certainly, I don't know if you've seen Stanislas Dehaene's book from about maybe 8 or 9 years ago. And he has a chapter on what we can only do unconsciously and what require another chapter on what seems to require consciousness. And, he's a global workspace theorist, but I think I'm not a global workspace theorist. But I think he's onto something. Maybe one of the evolutionary functions of consciousness comes in with talking to yourself, reasoning, using verbal reasoning. And maybe that requires consciousness. There certainly are some things that we, for example, one-step reasoning seems to be something you can do unconsciously, and perception seems to be something you can do unconsciously. But more complex reasoning seems to require consciousness. So maybe it's that talking to yourself and complex reasoning that is one of the evolutionary functions. Another function that people have speculated on is motivation. So I think, we just don't know. We don't know what consciousness is in the brain or why we have it. But there are various speculations we can have.
Maybe one additional question. I'm trying to understand the way on which this type of reasoning put us, because I think that on some of your articles you arguing that some types of functionalism are very close, dangerously close to panpsychism, when they ascribing consciousness or phenomenal consciousness to considerably simple systems such as computers, etc. And I think that here we at another type of road or type of way to panpsychism, when we can't say why phenomenality appears, but we already in the start of perceptual processing in the visual zone of V1, and there is no way to explain where the phenomenality comes from. There's no complex mechanism before that. So we should accept that phenomenality was in cells already. Maybe it's already very not panpsychism, but very strange form of theory of consciousness. And I'm trying to understand how we can run from it, how we can. I'm not trying to ask a concrete answer for this problem, but I'm trying to. Can you formulate some varieties of positions that can run from this problem? Because I can't. I'm trying, but I can't.
Yeah, so there are quite a number of experiments that are try to isolate when in processing the representation first becomes conscious. And one paradigm. Here's a paradigm that seems to make some sense. The experiment is you show a subject. I think I mentioned this in the article in the book. You show a subject a ring with little discs on the ring, and the ring goes around the edge of the visual field, and the subject's task is to tell when one of those discs becomes slightly darker. And that results in inhibition of attention to the center of the screen, because the subject is attending to this ring around the edge of the screen. And then you can have some constantly changing lines in the middle that sometimes form a figure. And then after showing the subject many of these, you can ask the subject, did you notice the triangle? Or, sorry, did you notice any figures? And the subject might say, yeah, I noticed a triangle. then you can look to see in the brain scanning what the difference is between the subjects who saw a triangle and those who didn't. And that gives you an index of the of when the consciousness first arose. And experiments like this suggest that consciousness arises around 150, 200 milliseconds in the course of the processing of the stimuli. And there's been many criticisms with that experiment, and the people who did this are now doing more complicated versions of it. But these things, you can get an experimental handle on these things, and once you can pinpoint the time of the first consciousness, you will know more about what consciousness is.
Okay, thank you. I see that Andrew has another question, and Alexander Gusev. So, Alexander, please, you can ask the question, and then Andrew.
Thank you, Professor Blok. Sorry if I misunderstood you, but my question is, it is right interpretation that this experiment shows that color perception not necessarily conceptual, so it is non-conceptual. But can we say what shape perception is necessarily conceptual?
Well, the infants can use shapes in reasoning long before they can use color. Now, whether that is perception or cognition is another matter. I believe that their perception of shape is also non-conceptual, but that they have concepts or proto-concepts of shape. So that's my take on it, but I think there's no definitive proof of that.
Yes, thanks. It will be new argument against Berkeleyan physics about you can't imagine first primary qualities without secondary qualities, but we can use this example like infants see shapes without colors, but I think it's not what you say.
I see. I think they see both shapes and colors, but they are able to conceptualize shapes before colors. So we have a disagreement about that.
Yes, it's not about seeing, it's about conceptual articulation. Yes, thank you.
Yeah, right.
So, Andrew, your question, please.
Yes, thank you. So if we use terms like conceptuality and non-conceptuality only for mental states, and if we have positive characterization only of iconic format of representation, and if the features like systematicity of thoughts and generality constraint can occur with iconic representations, could we have some kind of positive characterization of the discursive format, not just the lack of analog magnitude mirroring, something which could help us individuate in discursive representation, which could help us understanding maybe its structure, because if we understand conceptuality only in the pragmatic and functional sense like you do, it seems like we don't have any resources for the positive characterization of the discursive format.
Yes, so I'm not know if you're familiar with the recent article in Behavioral and Brain Sciences by Quilty Dunn and a few other people, Quilty Dunn and Mandelbaum.
Which one?
It's about the language of thought. I forget the exact title. Came out about a year ago. If you go on my website, you'll see my response to them. Or if you send me an email, I can email you their article. But they list 6 properties of discursive representation. and I think some of them apply to perception too. But the ones that are most significant, I think, are subject-predicate form and what sometimes is called inferential promiscuity. It's free substitution as premises in reasoning. And they have a couple of other ones that are good. I forget what they call it, but that the symbol can, the same symbol can be used in different roles. I think it's called role filler independence. So they have a few like that. So those strike me as, some of those strike me as pretty good for use in characterizing discursive representation. So yeah, I thought that was a very good article. But I have some disagreements, and my reply is on my website.
Thank you.
So there is no question, but I have one little last question. It's if we consider your argumentation in the context of modularity, can we say that it refers to my first question that I asked today? Can we say that there is some functional relations between some units in infants from 4 to 6 months when they consider colors. But these relations are modular, so they are just closed to any interactions with higher order cognition. And but in the sense of relating to each other, they are functional in some sense, because we can see it affects the attention. So in some sense, maybe not in the sense that you use the term functional, but in other sense, it's functional because it this way or another, it's something relate to attention. It relate to to maybe preferences or maybe reactions of that infant has. So can we say that it in some sense concepts maybe exist in infants, but it's modular, so it is closed for cognitive approach, and that these concepts just in 11 months or later they are becoming able to operate these concepts which are not been able before.
Yeah, that's certainly a possibility. I guess before I would want to, and I agree that some amount of modularity is certainly right. But I think before you postulate these concepts, color concepts, as being present in a closed module, you have to have some reason to believe it. I think what you say is a possibility, but I don't have any reason to believe it. So if you, in the absence, a lot of the work involving infants is you've just got to go from absence of evidence to evidence of absence. If you don't have any evidence for something, at least tentatively you suppose it doesn't exist. So that's the methodology that I'm following.
Thank you for your answer. So there is no another question from participants.
Yeah, well, I want to thank all of you for asking good questions, and I wish you luck.
Thank you, Professor Blok, for participate our section on conference. We hope that you can join our another conference maybe in future or maybe
Sure.
seminars.
Yeah.
Many thanks, and the next speech will be mine, but it will be in Russian. So if you
I think I'll log out.
if you don't mind, I'll send you the short thesis of some participants on English,
Okay.
so you can
Sure.
maybe say a few words about what you think. We'll be
Uh-huh.
very pleased about it.
Okay, great. Thank you. Bye-bye.
Thank you very much. Bye.